everyone. This work is also about jailbreaking, but it's like jailbreaking a group of LLM agents. So this work was done like in my internship in CI Lab, and also currently I'm a student at CMU. So as mentioned by like other researchers before, so like multi-agent LLM-based environment, it has like higher capacity, and previous works has demonstrated that they have like enhanced reasoning ability. And also they have like a lot of interesting wide applications, and they can really help us like doing the coding or like designing games or playing games. That's why we really care about those environments. We all know that the LLM jailbreak is feasible, like the gradient-based one, like GCG, and the query-based one, like tree of attack. And also, there are some works working on like LLM agent in multi-ground. Like for example, like PRP demonstrates like we can jailbreak the LLM like in 2 rounds. And also, there are like VLM-based agents, which name is like Agent Smith. It demonstrates that by retrieving the same adversarial image, we can jailbreak like VLM, a lot of VLM agents at a time. However, we want to investigate like how vulnerable it is for a group of LLM-based agents, because like VLMs, like it optimize all the things in the image area, so it's like 10 to the 9 times like the higher dimension than the image space. So here we propose like 2 threat models. The first is that we have a group of like 8 LLM agents. So at first, there's only one bad agent that's saying some harmful words or some bad words. And then we wonder at the end if all the agents can be compromised, like they can repeat the same like harmful things, or just as in this example shows. So the second threat model is that it's in a more practical sense, like LLM with safeguards. So we have a answering agent, but we also have like 2 safeguard agents. It's like detecting if the prompt is harmful or not, and also rewrite the prompt if the prompt is harmful. And this is the settings. So we have up to 8 agents, and their talking order can be either random or given, or it doesn't matter. And also, each agent, it has its own prompt or system prompt, and they have their own like cache. And also, we only do the intervention once at the very beginning. So we can get the middle some input, or we just don't get them. It doesn't matter. So basically, we are answering this question: is can a single bad agent corrupt like anyone else? So we found that like previous very state-of-the-art methods like GCG, AutoDan, ADC, and also the one like last speaker mentioned, like they doesn't have any success on our scenarios. So we want to answer questions like why they fail in this scenario, and what is the main difference between our scenario and the previous like single jailbreak attack. So at first we want to analyze like what's the key to success for like previous optimization methods. These are the algorithms for GCG and ADC. So just like from our perspective, like GCG is mainly a success because it has a really big batch, and also it do the coordinate change, like only change one coordinate at a time. And also for ADC, it starts from a continuous space and finally like regularize it to the discrete space. And also using momentum is really important for getting more information from the path gradient. So the biggest difference between our scenario and the previous jailbreak attack is that we want the harmful suffix to be extremely generalizable to, very, very diverse contexts. For example, like the system prompt can be changed, the role prompt can be changed, and their history cache can be changed, like can be very diverse. So this requires us to like train or to optimize the suffix on a big ensemble number, and this makes the optimization really, really hard. And also the adversarial suffix can appear like at different spaces. If it's only appear at the end of the sentences, it makes the optimization like easier. But if it appears at the beginning or the middle sum, how can we make the suffix still infectious? And we further analyze like why previous optimization methods fail. So for GCG, like we observe that it cannot arrive at a small loss area. Like the loss is always large, and this is like 2 or 3 times of the loss of the method we propose. So the main reason is that it gets less information from the gradient. So every time it samples a new coordinate and it samples a new like value for the coordinate. So though it uses the gradient, but it's kind of like a search-based method. And for ADC, we just find that since it's using the gradients from the continuous vector, but it's finally projected to a discrete vector, so there's a gap there. So for when the loss is small, the gradient is less accurate there. So here, we want to design a method that if the loss is large, then it relies like more on the gradient so that it can converge fast. And if the loss is small, we want it to rely like less on the gradient so that we can do searching. But we want to do it in a unified version instead of in a like very ad hoc version using threshold. So we just take advantage of the previous methods, and we use like big batch size. We update only one coordinate at a time, and we start from continuous space, and we use momentum. So this is the algorithm we propose. So it is like both search-like and gradient-based. And so the results is pretty nice. Like for some models, like we can achieve success. Like one bad agent can compromise all other agents, and the N means like the average number of infected agents through the whole process. And we can see like previous methods, the average is like less than 1. So it's like really, really like decreasing, but like our methods have a larger N. And to compare our optimization methods with others, so we also done a lot of other settings like first order or second order. Details can be found in the paper. And the main contribution here is that first we find a way to propagate and attacks like through very virus context and through a large collection of agents. And also we can bypass the safeguards. And the takeaway here is that for optimization, maybe like if we combine search-like with the gradient-based optimization, then we are like closer to success. And also, there are some key points for optimization, like big batch and dense to sparse. And of course, we have some limitations, such as like all the gradient-based methods, they have high perplexity, high entropy. And also, we shows like very little transferability to black bulb like methods. So we can discuss this later, and we're working on further works. Yeah, that's all. If there are any questions, yeah.